The sliding window trick behind computer vision is what we are considering in this video. Now, so we talk about the sliding window trick behind computer vision. From the last in the last video, we saw how AI sees images. So this is a continuation of that. By the end of this lesson, you should be able to explain why traditional neural networks are inefficient for image processing, understand the idea of a sliding window, describe what convolution means, explain the purpose of kernels or filters, perform convolution manually. We did a bit of all this in the previous video, compute output image sizes, understand stride and padding, explain feature maps, implement convolution in Python, and understand how convolutional neural networks recognize images. Now, the motivation for this is this. One of the biggest breakthroughs in artificial intelligence came from a surprisingly simple idea that instead of looking at an entire image at once, look at one small region at a time. I demonstrated that using a kind of matrix in matrix view in the last video. So this idea is called the sliding window trick, and it is the foundation of convolutional neural networks or CNNs. So modern systems for facial recognition, self-driving cars, medical diagnosis, satellite imaging, and handwriting recognition all rely on this simple principle of convolutional neural networks. Now, why traditional neural networks struggle with images? First off, before learning about convolutional neural networks, let us understand why ordinary, fully connected neural networks are not suitable for image recognition. First of all, images are large. Generally, images are large. So suppose we have a grayscale image of just 28 by 28. The number of pixels will be 28 times 28, which is 784. Now, a fully connected neural network first converts this image into a vector of length 784, which is pretty big. So if the first hidden layer contains 100 neurons, then the number of weights will now have to be 784 times 100, which is 78,400. Now, this is already a large number. Now, consider a color image of size, say 224 by 224. Since RGB images have three channels, so we have 224 by 224 by 3, which is 150,528 input values. Now, connecting this to only 100 neurons requires 150,528 multiplied by 100, which is 15,052,800 weights. So that is over 15 million parameters before the network even begins learning at all. So no learning yet, but then the system already has to deal with more than 15 million parameters, in fact. Now, the problems are as follows. Traditional neural networks suffer from several challenges, including huge memory requirements, extremely slow training that is, high risk of overfitting, loss of spatial information, and poor scalability for large images. We saw the ideas like this in the last video too. Fortunately, convolutional neural networks solve these problems using the sliding window idea. Now, first of all, images contain local patterns. So human beings do not recognize an object by examining every pixel simultaneously. Instead, our eyes naturally focus on small regions. For example, when recognizing a cat, we first notice the ears, the whiskers, the eyes, the nose, and the fur texture. And our brain combines these small observations into a complete understanding of the object. And then convolutional neural networks imitate this behavior of how humans see things. So our brain combines these small observations into a complete understanding of the object, and CNNs imitate this behavior. So instead of processing the whole image at once, they process one small region after another. This allows the network to learn the edges, the corners, the textures, the curves, the object parts before recognizing the complete object. So this principle is called local receptive fields. Now, a neuron only observes a small neighborhood rather than the entire image. So just a small neighborhood instead of the entire image. Now let's talk about the sliding window concept. Imagine placing a small square over an image. For example, you have a 3 by 3. The square covers only a small portion of the image. Instead of remaining fixed, it slides across the image. So the movement follows this pattern. It can move left to right, one step at a time, then down one arrow, and repeats until the entire image has been scanned. So every location is examined independently. Now, because the same detector is reused everywhere, CNNs require far fewer parameters than fully connected neural networks. This simple scanning mechanism is called the sliding window trick. It is the foundation of every convolutional operation. Imagine if we come here and try to demonstrate the whole idea of convolutional operations. So imagine you have, let's say, Okay, let me just go as much as possible. And we have this. So this has how many rows? One, two, three, four. So we have a 4 by 1, 2, 3, 4, 5. A 4 by 5 kind of thing. I mean, just for explanations. Now imagine that you now have a 3 by 3, a 3 by 3. Okay, I think this is better. You have a 3 by 3 matrix moving over this. So first of all, the 3 by 3 matrix takes care of this portion. And after sometimes, so it looks at this place and then it slides this way and covers this other region. Another 3 by 3. No, that's not 3 by 3 now. So it moves one step, right? So moving one step means that so from here now it then moves like this to cover another 3 by 3 this way. So you have another movement. So it takes a snapshot. Then after doing that, it moves over here one step again to go 3 by 3, taking a snapshot of this, another 3 by 3 this way. Then it can move down. Okay. So if 3 by 3 is exhausted here. So here it can then move down this way. So it's like it comes. Okay, let me check. Let me do this. So it then moves down here, another 3 by 3. Then it slides over here and then another moves another step, say this way. And each time it's making all that journey, it's actually taking snapshots of every region like that. So that's exactly the idea of the sliding window concept. So the movement follows this pattern left to right, one step at a time, then down one row, and repeats until the entire image has been scanned. So every location is examined independently because the same detector is reused everywhere. Instead of looking at the whole image, right? CNNs require far fewer parameters and fully connected neural networks. So this simple scanning mechanism is called the sliding window trick. It is the foundation of every convolution operation. So it goes through portion by portion like that, and then there's now a convolution of everything together at the end of the day to have a full picture of the image. Now we talk about a kernel like in the other video. So a kernel, also called a filter, is a small matrix that searches for a particular feature. I mean, that 3 by 3 thing I moved around is actually like a kernel. So it's what is called a kernel. So a common kernel size is 3 by 3. For example, you have this kernel to be 1 0 minus 1 1 0 minus 1 1 0 minus 1. So this kernel designed to detect vertical edges. So you see 1 1 1 down, 0 0 0 minus 1 minus 1. So that detects vertical edges. Other common kernel sizes include 3 by 3, 5 by 5, 7 by 7. Modern CNN architectures usually prefer small kernels such as 3 by 3 because stacking several small kernels captures complex features while reducing computational cost. So like what I described the other time, did I put that off? Okay. Let me go back to this. So what I described the other time, moving across this 4 by 4 thing. So, it takes 3 by 3 here, takes a picture, moves here, takes another picture, moves here, take another picture, and then moves down, takes a picture, then move one step, takes a picture, and then move another one step, takes a picture. Then each picture, all the information gathered in each frame like that is then stacked together. That's basically the idea here. Now, um, so like I said, modern CNN architectures usually prefer small kernels such as 3 by 3 because stacking several small kernels captures complex features while reducing computational cost. So, how a kernel then detects features. So each kernel specializes in detecting one visual pattern. Examples include vertical edges, horizontal edges, diagonal edges, curves, circles, textures, repeated patterns. Suppose we use the kernel K, which is designed for vertical edges like this. So when this kernel passes over a vertical edge, the multiplication produces a large positive or negative value. When no vertical edge exists, the output is close to zero. Therefore, um, large outputs large outputs values indicate the desired feature is present, while small values indicate its absence. Each kernel behaves like a tiny feature detector. So each kernel is a tiny feature detector. Now let's look at a manual convolution example. If you consider this image two with matrices with this matrix I, 210, 311, 022 for the row. So suppose the kernel is K is 1001. So this is a 2 by 2 kernel now. So the first window, so if you put it over this now, the first window will be 2131. So if you multiply corresponding entries now, so 2131. So you're multiplying corresponding entries, you're not multiplying matrices. So it means 2 times 1, then 1 times 0, then 3 times 0, 1 times 1. That's what we have here. So that is equal to 2 plus 0 plus 0 plus 1, which is 3. Therefore, the first value of the output feature image is 3, like that. So this is putting this 2 by 2 over this image. So if you move it here, you have 1011. So you also multiply out like that. So the kernel now slides one step to the right and repeats the same computation. So it moves from here and then it moves over to 1011 like this. So eventually every valid location produces one output value, forming the complete feature map now. So as I multiply out the if you so that multiplication is actually the convolution and it results to the feature map. Now, understanding the feature map itself now, the output produced after a kernel scans an image is called a feature map, also known as an activation map. So a feature map is a new image that records how strongly a particular feature is detected at every location. For example, large positive values indicate a strong match. Values close to zero indicate little or no match. Negative values may indicate the opposite pattern. So if the original image has dimensions n by n, and we use a kernel of size f by f with stride s equals 1 and no padding, then the output size will be n minus f plus 1 times n minus f plus 1. So n minus f plus 1 by n minus f plus 1. So for example, if imagine you impute this image and a 5 by 5 image, and then the kernel is 3 by 3. So output feature map will be 5 minus 3 plus 1 by 5 minus 3 plus 1, which is 2 plus 1, 3. So that'll be a 3 by 3. So each kernel produces one feature map. So a CNN with 64 kernels, therefore, produces 64 different feature maps. So each highlighting a different visual pattern. So let's look at a step-by-step sliding window movement now. So consider the following image with, I mean, numbers 1 to 16, pretty much. So each row, 1, 2, 3, 4, 5, 6, 7, 8, 7, 9, 10, 11, 12, 13, 14, 15, 16 for the 4 rows. Suppose we use a 2 by 2 kernel. So it means the first one is going to be over 1, 2, 5, 6. The second will be over 2, 3, 6, 7. The third will be over 3, 4, 7, 8, like that. So position 1 for this 2 by 2, the sliding window moves in this order, right? So position 1, you have 1, 2, 5, 7. You have that here. Position 2 is 2, 3, 6, 7, which you have here. Position 3, of course, will be 3, 4, 7, 8. That's position 3 here, 3, 4, 7, 8. So after reaching the end of the first row, the kernel moves down one row. So it moves down one row. That means that it comes to 7, 8, 11, 12 like this. So it moves down one row. 3 4 7 8. So I mean 7 8 11 12 for the next position now. So eventually every valid location is visited. So the kernel never skips pixels unless the stride is greater than 1. So at a stride greater than 1, so you just move one step at a time, right? Stride 2 means you move 2 steps after each one. So this systematic scanning process allows convolutional neural networks to analyze every part of the image efficiently. So example of convolution then becomes this. So if you consider the image 1, 2, 3, 4, 5, 6, 7, 8, 9, and the kernel 1001. So the first window will be 1, 2, 4, 5. Then multiply elements wise. So with the kernel now, so you have convoluted with k will be 1 times 1 plus 2 times 0 plus 0 times 4 plus 1 times 5. And then all of that results to 6. Step 2 now, you move to 2, 3, 5, 6. So from here, you move to the right, 2, 3, 5, 6. You also do the multiplication like that. For 2, 3, 5, 6, you have 2 times, 101. So that's 2 times 1 for the kernel, 3 times 0, 5 times 0, and 6 times 1. You get 8 for that. So if you repeating the process for all valid position gives the feature map this. So you do 1, 2, 4, 5, you move to 2, 3, 5, 6. You move a step down, you do 5, 6, 8, 9. You move another step down, you have 4, 5, 7, 8. So, of course, for 5, 6, 8, 9, if you do that with 1 and 1, so that'll be 5 plus 9. So that will give 14, right? So that gives 14 for this corner here. For the last one, now you now move from 5, 6, 8, 9 to one step here. That's 4, 5, 7, 8. So that'll be 4 plus 8, which is 12. And that is why you have 6, 8, 12, 14 right here. So this is exactly how convolution is performed inside a convolutional neural network. And then we move on to convolution as element-wise multiplication. So convolution will be, so convolution is based on two simple operations then. So first of all, you multiply corresponding elements and then you add the products. So suppose A is 1, 2, 3, 4, and B is 5, 6, 7, 8. So the convolution output is then 1, 5. So 1, 5, 2, 6. So A is 1, 2, 3, 4, right? And B is 5, 6, 7, 8. So you have 1, 5, 2, 6, 3, 7, 4, 8. If you calculate all of that, you then get 70. So in general, if the image region is I and the kernel is K, then the convolution output is then summation over I over J of I sub ij, K sub ij. This operation is called the dot product between the image patch and the kernel. So the larger the dot product, the stronger the detected feature. So we have a Python implementation right here. So you have an image 210, 311, 022, and you use a kernel this. So if you do that, so the first you have 2131, the second you have 1011, the third you have 1122, the third you have 3102. So of course, so for this now, this is just going to be 2 plus 1, 3. This is going to be so this is 2 plus 1, 3. This is 1 plus 1, 2. This is 1 plus 2, 3, and this is 6. And that is why is it, oh, that'll be 5, right? And that's why you get 3, 2, 5, 3 like that when you run that. So, and with that in place, then you have that. This simple program demonstrates exactly what happens inside every convolution layer of a convolutional neural network. So, deep learning libraries such as TensorFlow and PyTorch perform the same computation but much faster using optimized hardware. So, of course, this is easy to handle because we have just we can easily do the maths. But in real life, you have larger sizes than this, not just the 3 by 3 thing with a kernel that is 2 by 2. So one important question is how large will the output feature map be? So talking about the output size of a convolution, suppose the input size is n, kernel size is f, padding is p, and stride is s. So then the output size is n minus f plus 2 times p, that's 2 times padding all over the stride plus 1. So example, if you have an input image of 32 by 32, the kernel is 3 by 3, the padding is 0. Padding is the number of zeros you add across to make up for the missing for the input when you use a kernel. So then the stride is 1. That's the number of steps you move right or down as you move around. Then the output is 32 minus 3 plus 2 times 0, of course, that's 0, all over 1. So that will simply be 32 minus 3, 29 plus 29 over 1, 29 plus 1, which is 30. Therefore, you have a 30 by 30 output. So in example 2 now, imagine that you have a 28 by 28 input image and the kernel is 5 by 5, then the stride is 2, so the padding is 0. So the output is 28 minus 5 all over 2. Of course, padding is already 0 plus 1. So you have 23 over 2. 23 over 2 is like 24 over 2, which is okay, let's say 22 over 2, which is 11. We knock off the decimal. So that's 22 over 2. 23 over 2 is actually 11.5. So you say 11, 11 plus 1, that's 12. Does the feature map has dimensions 12 by 12 as opposed to what you started with? So understanding this formula is essential when designing CNN architectures. So understanding the stride now. The stride determines how far the kernel moves after each convolution. So instead of moving 1 pixel at a time, the kernel can move 2 or more pixels. So if s is equal to 1, the kernel moves only 1 pixel at a time. So you just move one step. So for this example now, if s is equal to 2, the kernel skips 1 pixel after every movement. So in this case now, so you move from here. So from this now you move 2 steps. So example, okay, I think this don't really do justice to what I'm trying to explain. So for s equals 1, now you move 1 pixel. For okay, yeah. So this is 4, right? And you have this. So first you cover this first two, and then moving one step for s equals 1 for the stride. So it means you move to this next one. So for s equals 2 now, you cover the first two, the next move will be so you don't move to the next one here, you just move to the next two, and that so stride equals 1, you move this way, and then after this you move to the next, you now move so the first one start from here, but here you're moving two at a time, so you have two and then you move to the next two. So that's when stride is equal to 2. So if in case you don't understand what I was talking about there, so like I demonstrated, so let's say this whole thing is a grid like that. So a stride of 1, so if you have a stride of 1, so let's say you have 2 by 2 here. Stride 1 will move to this place for a 2 by 2. But a stride of two will move straight here. A stride of two will move here. So it won't move one step at a time. It moves all over the whole place like that. So that's the kind of thing we're talking about. Now, larger stride has several effects. So it has small output feature map, so you don't have too many things to deal with. So that means faster computation, lower memory usage, less detailed feature extraction. Suppose the input image has 7 by 7, the kernel has 3 by 3, and S is equal to 2, so you're moving two steps. So the output size becomes 7 minus 3 all over 2, no padding, plus 1. And that would be 7 minus 3 is 4 over 2, 2 plus 1, 3. Therefore, the output feature map has 3 by 3 dimensions like that. So, choosing an appropriate stride involves balancing computational efficiency with feature preservation. So, though you have a smaller feature map, with a bigger stride, but sometimes you may lose some vital information. So you want to be sure you are choosing the appropriate stride. Now, understanding padding now. When convolution is performed without padding, the kernel cannot extend beyond the image boundaries. So as a result, boundary pixels are used fewer times. So border pixels rather are used fewer times. So information near the edges is gradually lost. So the feature map becomes smaller after every convolution. To solve this problem, CNNs use padding. That's convolutional neural networks use padding. Padding adds extra pixels around the image. So the most common choice is zero padding, where zeros are added around the border. For example, the original image is 1, 2, 3, 4, 5, 6. 7, 8. After adding one layer of zero padding, so if you add one layer of zero padding, so from this 3 by 3 now you now have a 4 by you now have so one layer of zero padding means you now have a 5 by 5 matrix. So before benefits of padding will include preserving image dimensions, so no information is lost in the process, improving edge detection, allowing deeper CNN architectures, preventing excessive shrinking of feature maps. Then you have multiple filters, learn different features. So a CNN rarely uses only one kernel. So instead, each convolutional layer contains many kernels. For example, you can have 16 filters, 32 filters, 64 filters, 128 filters, or 256 filters, and so on. So each filter specializes in detecting a different feature. For example, filter 1 can detect vertical edges, filter 2 detects horizontal edges, filter 3 detects diagonal edges, filter 4 detects corners, filter 5 detects curves, and filter 6 detects textures. So you say 1632 like that, and so on. So if a convolutional layer contains 64 filters, then the output consists of 64 feature maps. So each feature map contains different information about the same image. So these feature maps are later combined by deeper layers to recognize complete objects. So it's more like you send many people to go and do a job, and then they come back and submit their reports, and then you compile the reports and you get the full picture of whatever has happened. So you then have convolution of color images. So color images, real world images are usually colored. So instead of one channel, they contain three channels. So you have red, green, and blue basically. So a color image therefore has dimensions H, W, and 3. H by W by 3. So a kernel must also contain three channels. For example, a 3 by 3 kernel becomes 3 by 3 by 3. So each channel of the kernel is multiplied with the corresponding image channel. The results from all three channels are then added together to produce one output value. So mathematically, if the output is summation for C equals 1 to 3, depending on the number of channels, right? For three channels here. So over I over J of IJC, KIJC. I sub IJC, K sub IJC. Although the kernel has three channels, it still produces only one value at each position. So multiple kernels produce multiple feature maps. This enables CNNs to detect complex patterns in full color images. So we have a Python example using SciPy here. Instead of writing convolution loops manually, Python provides optimized functions. So the SciPy library contains the function convolve 2D, that's two-dimensional convolution. So here you have you import numpy as np, that's for numerical computation. Then scipy.signal, you import convolve 2D. So you now have your image now 2101, a 4 by 4 image. So you have 2101, 3112, and all that, and use this kernel which detects vertical images, vertical feature. So the feature map then you have the convolution of the image and the kernel, and using a valid mode, so you can then print the feature map. Of course, we know how to do this now. So you have 101. So the first movement is over this now. So here you have 2 and 3. 2 times 1, 3 times 1, that is 5. Then of course the zeros just cancel this out. Then coming over this now, we have -1 here. So you have, okay, this is -1, -3, and this is 5. Uh, is that okay? Okay, that this is for feature map now after the whole convolution. So in this corner, it's minus two. Should that be minus two? This is 2, 3. Yes, that's 5. And then here you have 0. Yeah, yeah, minus 1, minus 2. This should actually be 2, not minus 2, I think. Yeah, I feel, so when we move to this other side now, we have 1, 1, 1 here. This is 1 plus 1 plus 2. That is 4 on this side. Then, of course, all this is 0. And then here you have 4 minus 4, 0. Yeah, this works. So I think this should actually be 2, not minus 2. Then if we move a step down, so it means you have this now. So this is 1 multiplying 1, 2, 3. That's 6 here. And then you have 6 minus 3. That's minus 3. So should actually be minus 2 here. So I guess something may not be right somewhere. So this should actually be minus 3. So like that. So the parameter mode valid means that convolution is performed only where the kernel completely fits inside the image. So if the kernel does not fit inside the image, we don't perform calculations. So deep learning libraries such as TensorFlow and PyTorch perform millions of these convolutions every second using graphics processing units. Now the question is how does CNNs how do CNNs learn their own filters? One remarkable feature of CNN is that humans do not design the filters. Instead, the filters are learned automatically during training. So initially, every kernel contains random numbers. For example, a kernel can just contain this kind of numbers now. All right. So it's more like some kind of should we say weight now? So kernel behave like some kind of weights. If you remember the idea of linear transformations when we talk about weights and biases. Now, during training, the image passes through the CNN. Predictions are made, the loss is computed, backpropagation calculates gradients, and gradient descent updates every kernel. So it's more like the learning process now keeps updating the kernel. So after many iterations, the filters gradually become specialized. So early layers learn edges, lines, and corners. Middle layers learn textures, shapes, object parts, and deep layers learn faces, wheels, animals, letters, complete objects. So this automatic feature learning is one of the main reasons convolutional neural networks outperform traditional image processing methods. Now, let's look at some applications of convolutional neural network kernels. The sliding window mechanism is the foundation of many modern AI systems. Examples include image recognition, face recognition, medical image diagnosis, self-driving cars, optical character recognition, satellite image analysis, industrial quality inspection, wildlife monitoring, security surveillance, robotics, augmented reality, and autonomous drones. So far, we have some key takeaways from this idea of the sliding window trick. So a sliding window allows a CNN to examine one small region of an image at a time. A kernel or filter is a small matrix that scans the image and searches for specific visual patterns. So the convolution operation multiplies corresponding entries and sums the result to produce one value in a feature map. So the output size of the convolution is determined by n minus f plus 2p all over s. So p is padding, s is slide, and plus stride rather, all of that plus 1. So where n is the input size, f is the kernel size, p is the padding, s is the stride. So we talk about the stride tells us how many steps to move as the whole as the sliding window moves. So padding helps preserve border information, while stride controls the movement of the kernel. Modern CNNs learn hundreds of filters automatically using backpropagation and gradient descent, allowing them to recognize increasingly complex features from simple images to complete objects. So the sliding window trick is one of the most influential ideas in deep learning and forms the backbone of nearly every state-of-the-art computer vision system today. So we have our practice problems, as you can see here. You can see questions 1 to 5. I get to solve 2 of this. So, and you can see that it's been maths all the way as we keep talking about AI. So I'm going to solve questions 4 and 5 here, interestingly. So I'll do 4 and 5. So, so we'll get there. So you can see questions, you should be able to see questions 1 to 10 at once. Let's see. Okay, that doesn't work. So let me just focus on showing you 5 at once. So you can see 1 to you can see 1 to 8 clearly here, right? You can see 1 to, in fact, 1 to 9. You can see 1 to, okay, let me stop on 1 to 8. You can see 1 to 8 clearly. Then you have 9 to 9 to 17 showing very well now. 9 to 8, 17. And finally, you have the rest. So I'm going to take questions 5 and questions, let's see. Okay, so let's start with question. Okay, I think I'll just take question 4 and answer question 5 to some extent and stop there. So let's go for question 4 now. Yeah, so for problem 4, it says a 128 by 128 image is processed using a 3 by 3 kernel, padding 1, padding 1, and stride 1. Calculate calculate the output dimensions. Calculate the output dimensions. Okay, so we want to calculate the output dimensions given all of that. So the solution here, okay, I guess I want to make this thicker. So for the solution, solution, the output of a convolutional layer is computed using output size equals n minus f plus 2p all over all over all over s plus 1. So here now we have that here n here n is equal to 128 based on what we have, 128 by 128. N is 128. F is 3. That's the kernel. The padding is 1. The stride is also 1. So, so we have the output size. Output size can then be computed as 128 minus 3 plus 2 times the padding all over the stride, which is also 1. All of that plus 1. So that's 128 minus 3 plus 2. 128 minus 3 is 125 plus 2, that's 126. Uh, all of that plus 1, right? So 128 minus 3 is 125. So 125 plus 2 is 127 all over 1 plus 1. So that is 127 plus 1, which is equal to 128. So in that case, we say hence, hence the hence the output feature, the output feature has dimensions 128 by 128. So because one layer of zero padding is added around the image, the reduction caused by 3 by 3 kernel is exactly compensated. So as a result, the convolution preserves the original image dimensions while still extracting local features. So padding can preserve what you have originally. So yeah, I think I want to stop there for this. So you can try out the other problems. So I'll try to flash those the practice problems here. I want to, so you can see 1 to 5 here clearly. Then you can see, okay, I think, okay, let me just show. So, okay, 6 to 10 is my focus here, 6 to 10. And then 11 to 15. And finally, the rest. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not, why not go ahead and do that right away? And as you subscribe, also hit the notification bell so you can always get alerted each time a new video is is released. So hit the notification bell so you get alerted each time a new video is released. Or you can also become a member of this channel by clicking on join. That gives you some special privileges to find out as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.